Okay, now we look at the, in one-dimensional optimization, we, all the algorithms we consider here can solve one-dimensional optimization of unimodal functions. Okay, so you should know what is the unimodal function. A unimodal function, a function f, a real function f of single variable is said to be unimodal in the interval from a to b if it has only one extremum within the interval. Extremum means it can be either the minimum or maximum. Okay, we have a generic word for that. It's what it's called extremum. Now, okay, these are the examples of unimodal function. Now you can see from this figures, from this figure, convex function is unimodal, but unimodal may not be convex. From this, so the convex implies unimodal. Okay, this is convex and unimodal, right? These functions are not convex, but unimodal. Okay. And then in okay. Now okay. For convenience, then we define the notation. We define fxk plus lambda sk as a function of lambda, right? For an n-dimensional for a real function of n variables. Once the point xk and the vector sk are specified, then xk plus lambda sk is only depends on only the scalar lambda, and therefore fxk plus lambda sk is a function of single variable. Okay, and what is the derivative of this? In the following algorithms, sometimes we need to know, or sometimes we require the derivative. Okay, so what is phi? The phi prime or d phi by the lambda is by using chain rule, right? From chapter 4, the phi lambda is equal to sk transpose squared fxk plus lambda sk. Okay, so when we do the when we do the when we when we find the minimum of a function, then if you want to know the phi prime or d phi by the lambda at any lambda, then this is equal to sk transpose squared fxk plus lambda sk. Okay. Now, how can we solve this? I think the proposition 5.1.2 give us some idea how to start. Okay. The idea is we start with an interval. The idea is in solving one-dimensional optimization, we start with an interval containing the minimum. Okay, and after that we reduce, okay, in some way we reduce the interval that contains the minimum until, okay, it converges to the solution. Okay, that's the idea. So you can see that this proposition provide a test. How can we choose an appropriate interval? And suppose the function f is unimodal. Okay, then the function f has a minimum within the interval within a given interval A to C if one of the following conditions holds. You can use either one or two. Okay, the first one is the condition on the slope, or that means you need to know derivative, whereas the second one, we don't need derivative. We only need to know the value of the function f. So what it is? So what we want to know is, you see that this is the minimum. Then what we need to know is that at the point A and C, the slope of f at the point A, or the left-hand side of the interval, is negative, and the right-hand side is positive. If you want to find a maximum, then we change the sign. Okay. Now you can see that this one, f prime A, is negative, and f prime C is positive. Okay. You have to do some search before. Okay. And then, in the second condition, if there exists okay, in the second condition, given an interval from A to C, then there exists a point B in between A and C. It doesn't have to be a midpoint. It can be any point between A and C, okay, such that FB is less than FA and FB is less than FC. So suppose this is A, this is FA. Suppose this is B, this is FB, and this is C. This is FC. Okay. So we have two situations in which we can guarantee that a minimum x star lays inside the interval from A to C. Depending on if you, in the algorithm that you use to solve optimization problem, if you have derivative information, then we use the condition A, right, which requires slope. And if you don't have information on the slope, or it's difficult to compute, okay, to have the information on the slope, then we prefer the condition B, which require only function values. Okay. Based on this algorithm, or based on this proposition, we will look at three methods for solving one-dimensional optimization. Even in MATLAB use these three algorithms. Even in any, I think if you go to the professional, the commercial software for doing optimization, for solving optimization, they use three of them, no more than that. Okay, to solve a single objective, single variable optimization. The first one is called the quadratic Okay, there are two categories. We have three methods. The method 1 and the method 2 belong to the same category, which we call curve fitting or interpolation method. Whereas in the second method, in the last method, is based on the sectioning method. The idea is sectioning method is similar to the bisection method. In the bisection method, right, you have the interval, but then in the sectioning method, we may not have. We reduce the interval with a different ratio. Okay. Now this one is called the quadratic interpolation. The idea of quadratic interpolation is this. If we have 3 points, okay, if we have 3 points, we can construct an interpolating polynomial. An interpolating polynomial is a polynomial that passes through all the data points. Okay, in making model, you see that given data points, there are many ways that we can construct a polynomial to approximate the data, right? But so there are many types of there are many types of polynomial that you can construct. Okay, and the interpolating polynomial is the polynomial that passes through all the data points. Okay, and it's called interpolating polynomial. So if we have 3 points, you can see that we can construct a quadratic function, right? When we have 3 points, we can construct a unique polynomial that passes through all the 3 points, and this is a quadratic function, right? So why we choose a quadratic function? Because a quadratic function has we have a formula, right? We have a formula to find the minimum of a quadratic function. Am I right? You see that this in this method, you start to see the idea of using an approximation to solve our problem. We don't know what the function is, but we know the value of the functions. Okay, we have three coordinates, right? A, FA, B, FB, and C, FC. So what can we do? What is the best we can do in this situation? And okay, we construct a polynomial that passes through all the points, right? Because if the polynomial is a good approximation to the actual function, then the minimum of the polynomial should be close, right? Should be close to the minimum of the real function f. That's the idea, and we find that this is pretty true. This is pretty true when the interval is not too large. Okay, so we point A, B, and C. With the point A and B and C, right? Okay, we have a function like this. Yeah, a function like this, fx, which we don't know what it is. But we know the 3 points. Okay. What we do is we construct a polynomial, a quadratic polynomial. Okay, and we call this one maybe the h of s, h of x. So h of x is an approximation which takes the form ax squared on alpha 2x squared plus alpha 1. I think in the slide, I think we use the capital A. Okay, let's follow the notation in the slide. The h is the, let me see. I think it's ax. Okay. A, B, C, right? Hx. Hx assumes the form a x squared plus bx plus c, right? Now, so what is the minimum of this object of this quadratic function? We know this from high school, which is what? Minus b over a, right? Minus b over a. Yeah. So the minimum of hx is at x equal minus b. Is it minus b over 2a, right? Yeah, minus b, oh, sorry, minus b over 2a. The h prime is 2x plus b, right? And we equate the slope to be 0. And then we have the x. Okay. So this is the minimum that we know exactly. Then now you can see that we can find the coefficient. Once we know the coefficients a, b, c, right? The coefficients, the small a, small b, and small c, then we can compute the approximate of the of the minimizer of the function f, right? By taking the minimizer of the quadratic function to be an approximate of the real function f. Okay, this is what we do. And once we, okay, and now if you want to derive, this is the formula. You can prove that, okay? The coefficients A, B, C, and I think you know already from the class linear algebra. We can construct the interpolating polynomial and solve and find the parameter, the coefficients A and B and C, right? We have 3 variables we have 3 equations in 3 variables. I think if you take the linear algebra with Ajahn Komut, I think she said that already. Did you, Ajahn Komut? The interpolating polynomial. That's a problem in which we apply a system of linear equations. Yeah, in EE math. Sorry, I think yeah. Sorry, because in your second year, Ajahn Komut was on a sabbatical leave. I'm sorry. Yes. Okay, but that's okay. And okay, here we have the coefficients. We compute that, and this is the analytic formula for the coefficient. And then, okay, now the idea is, okay, I think the point here is not to derive the formula. We have already the formula, okay, And then, so what happens then? When we, after we are at the point, okay, a given A, B, C, right, and FB, FA, FB, FC, we can compute the approximate of, okay, we can compute, this is the formula you use. The lambda tilde star is the approximate of the minimizer of the minimum of the function f. Actually, the lambda tilde star is the minimum of the approximate quadratic function. Okay, then what happens? You see that it may, okay, when the interval from A to C is not small enough, then the lambda tilde star may not be close to the minimum, okay, to the minimizer of the function f, but that doesn't matter. But the point is, you say that to bracket the minimum using only functions value, we need 3 points. We have, first we start with A, B, C, right? And once we compute the first, the lambda tilde star, now we have 4 points. What does it mean? So with the 4 points, that means we only need 3 points to bracket the minimum. That means 1 point is redundant. So when we compute the lambda tilde star, then we compute the function, and then we compute the value of f at the point lambda tilde star. Okay, this is the computation that you need to do. So then, okay, so then we have 4 coordinates. How can we get rid of one of them? Because if we get rid of one of them, you see that lambda tilde star, I think it can be proved in theory that if FB is smaller than FA, is less than FA, and FB is less than FC, then lambda tilde star that we compute must be within the interval from A to C. It's guaranteed. Now we have 4 cases. It may, okay, then we, to understand this, there are 4 possibilities of it. Then we have, first, we have okay. Here you see we have FA, FB, FC, right? So first, lambda tilde star. The first possibility is that lambda tilde star is between A and B. Right? And the second possibility is that this is A, B, C. Lambda tilde star may happen to be within okay, within B and C. There are, first we have 2 possibilities, right? And then in each possibility there are 2 cases. When lambda tilde star is in okay, when lambda tilde star is between A and B, there are 2 possibilities. F lambda tilde star may greater than FB, or F lambda tilde star is less than FB, right? F lambda tilde star is less than FB, or F lambda tilde star is greater than or equal to FB. Right? There are only 2 possibilities, and these 2 cases can occur in one of them. So totally we have 4 possibilities. This is case, we call case 1. Case A, case A, case A, and this is what we call the case B, right? In case A, in each of case A and B, then there are 2 choices, right? And therefore we end up with 4 possibilities. Right? If f lambda tilde star is less than is greater than fb, what happens in for the case A? For the in case A, if f lambda tilde star, sorry, if f lambda tilde star is less than fb, then that means we don't need fc. Right? If f lambda tilde star is greater than fb, then that means we don't need fa. We don't need a, right? We replace a by lambda tilde star, right? And fb and fc remain the same. Okay, and then you can write it down. And then we do the same with the case B. Then the case B we split into two sub. Okay, another 2 possibilities, and therefore this is we have 4 possibilities, and they all are summarized in this table. And so this is from this table. Okay, when each of them, so you have to need to write the program to check. We use if then statements, right, to check 4 cases. Okay, and then okay, that's what you do. So now the point, the rest of this is that once we eliminate, okay, now you know how to eliminate a redundant point. That means now we can reduce. After we compute lambda tilde star, we have 4 points, right? Once with 4 points, we can eliminate one of them, either on the left-hand side or the right-hand side, right? Depending on the situations. And so now that we can reduce the interval that brackets the minimum smaller. The interval that brackets the minimum is smaller, right? And then if this, okay, and how can we know that we reach the minimum? Now you can see there are, if I think we keep doing this. So if the minimum of the approximate, that means if lambda tilde star is getting closer and closer, right? Then you can decide to terminate the iteration. That means it converges. And I think in theory, the convergence rate of this method is superlinear. R is more than 1, is more than 1 but less than 2. Okay. Or there is another method in which you can, because you know the f lambda tilde star, right? And if the minimum of the approximate quadratic function, you see that because we know h, function h, then we can compute the minimum of the approximate quadratic polynomial. Am I right? We construct the polynomial h, and we know all the coefficients a, b, and c, right? So when we know this, then we can compute the minimum of the approximate h of x, right? We can compute the quadratic approximant h, right? If this, so at the point lambda tilde star. So if f at the point, so if f lambda tilde star is close to the edge of lambda tilde star, right? Then that means this is another sign that it converges to the point. But normally, I think we don't do this because normally I think we do the iteration that's faster. Because normally it takes more than one iteration to do unless the interval is very small. Okay, but if the interval is and when the interval is very small, that means you are getting it already to the solution, right? Okay, and so this is the first method, and the second method was proposed by David. You will, I think, in this chapter, you will hear these names. I think they are what we call they are considered of they are considered of the or the moment. Let me think. They are considered great people in numerical optimization, and they are. Michael Powell was a professor in numerical optimization, and he made a lot of contribution, okay, to this subject. And as you will see later, okay, and I think I had a chance to I met him twice. Okay, when I visited him in let me see, in 1996, I visited him in Cambridge. Okay, and I met him again in Beijing in a conference in Beijing in 2006, and later I think a few years, I think after 2010, sometime. Okay, and he passed away. So, okay, and the second method is a cubic interpolation. The idea of cubic interpolation is similar to quadratic interpolation in the sense that we start with that interval A to C that brackets the minimum, okay? But here in cubic, we use a derivative. We use slope. We use we use slope information. So okay, if you have an interval from A to C and you know that f prime A and f prime A is negative and f prime B is positive, right? That means the interval is guaranteed to be inside this interval, right? So then because we have slope and we have the value of the function f, then that means we can, with the four informations, right, with the fa, f prime A, fb, f prime B, we can construct a cubic polynomial. We can construct a cubic interpolating polynomial as well. To construct a cubic interpolating polynomial, we need four pieces of information, right? If you use the function values, then that means you need to know the value of the function f at 4 points, 4 different points. But if you have the function and the derivative, then you only need to know the function and the slope at only 2 points, like what we do in this situation, right? With this, then we construct a cubic polynomial, and this is possible to do that. Okay, we can derive an analytical formula for computing a cubic polynomial. Now the rest, and then The idea is similar to the quadratic. If the cubic interpolation polynomial can well approximate the function f, then the minimum, then the minimizer of the cubic interpolating polynomial should be very close to the minimizer of the actual function f, right? That's the idea. Okay, and it works. It really works. And here is the so we derive. We assume this is the cubic interpolating polynomial that passes through the point A and B, where we know f prime A, fb, f prime B. And this is the formula for computing the minimum of the approximate h of lambda. Okay, so once we know once we know f prime fa, f prime a, fb, f prime b, right? Then we compute the lambda tilde star using the formula 5.3. And with this, then, now that's easy. Now you can see that now once we compute the f lambda tilde star, once we compute f lambda tilde star, then now we have 3 points. We only need 2 points, right, to bracket the minimum. Then that means we can get rid of one of them. How? So after obtaining lambda tilde star, we compute f, the function f and the slope at that point. So after obtaining lambda tilde star, we compute f of lambda tilde star and f prime at that point, right? With the derivative. Now with the derivative, right? Then you can decide if the derivative is positive, then that means we replace b by lambda tilde star, right? And if f prime if the slope at the new point is negative, then that means you don't need a. We replace a by lambda tilde star. Then the interval is reduced. Okay, and I think there are details in deriving this, and you can see in the reference by in the book by S.S. Rao. Okay, and the details is in that book. And now, because you see, if the slope of FA is negative and the slope of FB is positive, then we can prove, we can guarantee that lambda tilde star will be within A and B. It cannot be outside. This guaranteed by theory. Okay, and this is why we're doing this, because I think here f prime A is negative and f prime B is positive, implies that lambda tilde star, we can prove this. This FA. Okay, we can prove this. Okay, then we keep doing this until what? Until lambda tilde star in the new iteration is close to the lambda tilde star at the previous iteration. or we know that here, because we know here in this method, we need slope, right? And we know that at the minimum, the slope is close to 0. Then you can choose either you can look at the slope at the f lambda tilde star. If it's close to 0, then you may decide to terminate the iteration, or if the new lambda tilde star is close to the previous value, then you may decide to stop. Okay. But you have to be very careful when you are comparing something to be 0, because here in this case, you may find that in practice, if you set when you check the if you check the slope of the function f, right? If you check the slope of the function f, right, and you set the and if you set the criteria to terminate the iteration, that if the slope or if the absolute value of the slope is less than epsilon, right, we decide to terminate. It makes sense, right? Theoretically, it works. Well, theoretically, it makes sense, but in practically, you have to consider the effect of Randolph error. Why I say this? Because I think you have to know this. Because if you set the epsilon to be too small, you will never achieve this, and therefore it goes into the program goes into the infinite loop. And this is not surprising. Okay, this is something you have to know. And from the viewpoint of computation, let's see what happens here. We use the Taylor series expansion again, and I'll show you why I say this. This can be proved by using by considering the Taylor's expansion of the function f. So fx star plus epsilon. What is the x star? The function f has the minimum at the point x star. This is the point x star, right? And the slope, the f prime x star, is 0, right? This is all of us know. Okay, so what happens here? If we look at the the Taylor's expansion of fx star plus epsilon, then you can see that fx star plus epsilon is equal to what? Fx star, which is something, plus f prime x star multiplied with epsilon, right? Plus 1/2 epsilon square f double prime am I right? Plus something. This is a high order term. Now you see that when epsilon is very small, what happens? Now the second terms, you see that the second term always go to 0, right? Because f prime x star is equal to 0, right? Then now what you can see is that fx star plus epsilon is equal to fx star plus 1/2 epsilon square multiplied with the second derivative, right? And if the epsilon is very small, then you can neglect the rest, right? Now you see that if x star is the actual value of the minimizer, and epsilon can be seen as an error, a small error in the, okay. Now you see that if we have the error, that means if we have the error, let's say if we have from this, then we see that if epsilon is about 10 to the power of minus 6. Okay, then you can see that what happens if epsilon is 10 to the power of 6. That means if we have the accuracy in the X star up to 6 digits, approximately, roughly speaking, then what is the accuracy in the value in the minimum of the function? Suppose that the second derivative has finite value. Now you see that if epsilon is 10 to the power of 6, which guarantees that x star plus epsilon is accurate to x star, right, up to 6 digits, approximately, right? Then you can see that the accuracy in the objective function is much less than that, because the second term of the Taylor's expansion is 0. That means the error in the objective function, in the function f is about in the order of 10 to the power of minus 12. 10 to the power of minus 12. So that means, so what does it mean? This suggests that if we have, you see that in MATLAB, okay, on computers, we can store real numbers with accuracy up to finite digits, right? If you, okay. I think in MATLAB or with a 64 bits computer, if you use a 64 bits, that means 8 bytes, right? If you use a 64 bits to store a real number on computer, this is pretty standard now. Nowadays we use IEEE standard of for floating point numbers. Then the accuracy is about, I think, is between 15 and 16 digits, 15 and 16 decimal digits. And this is if this is what happens now with in MATLAB. Okay, you see that's the precision. When you type epsilon, the epsilon is the value of the accuracy in floating point arithmetic operations. Okay, epsilon is the value is the maximum value of real number such that 1 plus epsilon is not greater than 1. Because normally 1 plus epsilon, if okay, for a positive epsilon, 1 plus epsilon is greater than 1, right? But if the epsilon is too small, computer cannot recognize this. They say that 1 plus epsilon is not greater than 1. And then you say that now that's the effect of the error. This is route of error. And in professional computation, this is you have to concern, or you have to take care of the error. Okay, that's why when we do computation, even if the program is correct, then the answers that you receive from computers may not be correct. This is something you have to be aware of when we use computers. And I'm sure, you see, I'm sure that many of you many of you never hear of this, right? But this is a well-known fact in using computers to do computations. Okay, so that means so if when you check the slope, okay, if you check the slope, if you okay, you have to be very careful about the value of the epsilon, because if you see with the 15 decimal digits or 16 decimal digits in MATLAB or in any programming language, if you use C, you just double. You have the float and double, right, for your variables. I think quad is optional. It's not in standard C. And in Fortran, you have the single precision and double precisions. Right? That's now I think it becomes standard with 64 bits computer. Right? We used the double precision. Okay. Then we have. Then you see on MATLAB, we have about 16 digits, 16 decimal digits of precision, not more than that. Then you can expect that that's the precision for computing the function f, right, in MATLAB. Then you cannot, it doesn't make sense if you expect to have the precision in the value of the function x more than half of the precision in the function f. That means if you make the precision, if you require precision more than 7 or 8 digits on double precision arithmetics, then it's hard to do that. And if you said that, or maybe if you require more than that, perhaps you will get into trouble because the iteration never iterates, never stops. The iteration never terminates. Okay, then you waste time in getting. Okay, you waste time more than you need. Okay, and that's the okay. This is the. Okay, we still have time for the golden section. Okay, good. Okay, now we go to the last one. The last one is similar to bisection method. Okay, the last one in this method and this golden section method is very reliable and it's easy to program, and you will find that many software, many commercial software, even MATLAB, use this as well. And sometimes in some commercial software, they use more than one method. They combine two, for example. And this is sometimes if you use the function value, then some people use the combination of golden section method with quadratic interpolation. The quadratic interpolation works very well when the interval a to c is small. Okay, is small enough. Then, but so before that, some people use they use the golden section method to reduce the interval. Okay, and until it's small enough, then they apply the quadratic interpolation. Okay, so what is the idea of the golden section? Have you ever heard of golden ratio? Golden ratio. It's a number. Golden ratio. Napak, have you ever heard of this? The golden ratio. What is it? I think the architecture knows this well. What is this number? We find this number in many in many things. In many things. If you okay, if you look and I think it's called golden ratio. I think in Greek architecture, we find that I think we find this ratio as well. I think Greek architecture is considered one of the most beautiful architecture, right? I think in Western civilization, you see people admire Greek architecture and Roman architecture. Greek architecture is known as the it gives you when you look at that, okay, the Greek architecture is pleasant, right? And this number appears in many Greek architecture, and that's why it's called golden ratio. And in this method, okay, we use this ratio as well, okay. Okay, now we will see how this ratio appears in this optimization problem. Now, the idea is very simple. Now you know that, okay, I'll write it down. Now you know that when to bracket the minimum using function values, we need 3 points, right? So that means let's assume that we have a primitive method. So the idea is we have FA, B, F, C. Here we have A, B, C, right? We have the interval A, B, C in which we know FA, FB, FC. If you want to reduce this, then you compute 1 extra point. Okay, we compute 1 extra point. Okay, we compute 1 extra point by any method. It can be a quadratic interpolation. It can be something. But let's say, okay, so we compute a point in between, right? We choose a point between A and C. Then we have 4 points, and we compute F at that point. You see, suppose okay, it can be between A and B or B and C. Doesn't matter. But suppose this is the extra point, which is called D. Okay, the point D. So from when we compute the point D, okay, with a method, it can be any method. Then, if you then now you can reduce the interval, right? From this example, you can see that we replace ABC by BDC, right? Am I right? Yes. Okay. In this example, we reduce. Okay, we replace interval. We replace ABC by BDC. We eliminate A, and therefore the interval is reduced. Now, if you want to reduce this again, what happens? Then you have to, let's say this is A naught, B naught, B naught, B naught, right? And then when you do this, okay, then we know from this, then that the B is replaced by A1. Okay, we use subscript. And this is B1, and this is C1. Okay, and then we make a D1 again, right? We make D1 again, and we compute D1. So you see that in each iteration, the cost per iteration is 1 function evaluation. In each iteration, given A, B, C, F, A, F, B, F, C. The cost in doing this is to compute F at the new point. So one function iteration is the cost per iteration. Okay, now the thing is, if you can keep doing this, but now the point is, can we do this by so that the interval is reduced at a constant ratio? How can we do this? How can we section? Okay, how can we do sectioning so that the interval is reduced with a constant ratio, with a fixed ratio, with a constant ratio, with a constant ratio? And this is how we derive the golden section method. Okay, this is how we derive a golden section method. Okay. Now, okay, once you understand the problem, then we go back to the slide. Then with the golden section method, okay. First, we begin with AI, BI. So we begin with AI, BI. Okay, to start with, but then we need to compute the two middle points. First, we compute two middle points. We call it x1 and x2, and we use superscript to denote the iteration. So here we have two points in between, not midpoint. We have 2 points in between. Okay, x1 is close to A and x2 is close to B. Okay, so we start with A and B, then we have x1 and x2 to begin with. Then after that, we do the section so that the interval containing the minimum is reduced with a constant ratio. And after that, the cost per iteration is only one function evaluation, not two. Here we begin with compute the. Here you see when we start. Okay, with the starting A and B, we have to compute x1, x2, right? So we compute the function value twice, right? But this only at the starting iteration. After that, you will see that we compute only one function event. Okay, we compute only once per step or per iteration. Now, in this figure, okay, this is A1 and B1, okay, and this x1, x2, superscript I, okay. Then with this, you can see from this that x1i, f at the point x1i is less than f at the point x2i, right? And therefore, what do? We reduce. In the next iteration, we eliminate B1, right? And we replace B1. We replace B by x2i, right? We replace B by x2i. Okay. Okay. Then if this interval is reduced with a constant ratio, you will see that x1i shares the same place as x2i plus 1 is the same place. So we only we only compute the new point as x1i plus 1. And we compute this, right? Compute this in the need to form the next iteration. Then we need only one function evaluation. Okay, and it happens like that all the time until it converges. now we'll see what is the ratio. If this is the if this is the all the requirements, we set up all the requirements as a mathematical equations, and to find what is the ratio. Okay, so then from this example we see if tau is a ratio. Okay, this is tau is the ratio to be determined. The tau is the ratio to be determined. Okay, so from look at this figure, we know that with the ratio is that this length is bi minus ai, right? Okay, and this is bi minus x1, right? Bi minus x19, right? And this also, this length is the x2 I minus ai. You see that the x2i minus xi is equal to v1i minus x1i. Okay, these two has to be equal first, and then the ratio of this length of the green of the length of the green line to the whole interval, which is the vi minus ai, must be equal to the tau, the ratio of tau. You see, and why this? Because you say that because we do not know that we don't know whether the interval will be on the. No, we don't know if we will eliminate the left or the right end of the interval, right? And this is why we set up this to be equal, so that it reduces with a constant ratio, right? And from this, then you see, and once we in this example, we eliminate, right? We replace b, the bi plus 1 is set to be x2i in this interval, and then with this interval, then you see that now the x1i becomes x2i plus 1, right? So again, the interval from, I think I used the orange line. The interval from this is the whole interval, right? This is the whole interval for the iteration I plus 1. And then the ratio of this must be equal. Okay? It happens like this. Then we can equate the equation, which is now eventually we arrive at this equation. Okay, by using all that. You can follow that, okay, later. But then the point is, we from this, okay, we can set up an equation which is -1 plus 1 over tau is equal to tau, right? And actually, this is a quadratic polynomial, which is the tau squared plus tau minus 1 equals 0, and we choose only the positive root, right? There will be two roots, the positive one and the negative one. We choose the positive one because here is the ratio. Ratio must be positive, right? A positive number. So, and we choose this is the positive root. This is positive root of the polynomial. Okay, so we know that the tau is approximately 0.16, and 1 minus tau is 0.382. Right. Then once we know that the value of tau, then we can form the algorithm for the golden section method. Okay, so if you see that when we first start the iteration, we start with okay, with A and B, with interval A and B, right? We compute x1, x2, right? And then we have fx1 and fx2. Then we compare. If fx2 is greater than fx1, then bi plus 1 is x2, ai plus 1 is ai, right? And x2i plus 1 is x1. And we set xi plus 1. We compute, this is the new point. Okay, then we and then for the next iteration, okay, to go to the next iteration, we have to compute f at the new point, because this okay, otherwise we set ai plus 1 to be x1i, okay, and bi plus 1 is equal to bi, the same, right? And then in otherwise, if okay, we compute the f2 xi plus 1 here. So this becomes a new point for the else case, right? And from this, then we do, this is the new point, right? And then we compute fx2i plus 1 for the next iteration. You see that why I say this. You may not see this at the moment, but the thing is, in optimization, most of the cost of computation depends on the time in computing the objective function f. You may not see this, but okay, for example, in power system, if the cost function is the loss in the total in the whole transmission line, how can we know the loss in the transmission line? We have to solve the network equation, the whole network, okay, so that you know the current in each branch, and then I square R is the okay in all is the summation of the I square R, right, is the total transmission loss for that. You see that to compute an objective function, you have to solve a network equation, and if the network is very large, okay, or if you want to do the optimization in a circuit, if your circuit has, let's say, 1,000 branch, to solve a circuit equation for 1,000 branches, it takes some time. It doesn't happen in 1 or 2 seconds. In textbook exercise, you don't say this because I give you the function, right? And it takes you just a fraction of a second to compute that. So you may not see this, but in real situation, sometimes it can take many seconds to compute the cost function. So we don't waste time. That means once you compute the cost function, the function f, and then if you want to use it later, you have to keep it. You have to store it in a variable. We don't recompute it. Okay, because if you keep doing that, then it can and then your program may take a long time. before you have a solution. So you waste computation time without getting any better results or doing nothing, let's say. And this is something you have to, this is something we have to consider as well. So when you write the program, once you have the function f, we store that. If you want to use it later, we use that variable. We don't recompute it. Okay, and I think in homeworks you will find that. So when we implement when we implement an optimization algorithm, what we concern is how many the cost. Okay, and the cost is measured by how many times you compute the gradient and how many times you compute the function, the objective function f. That's the cost. We don't measure the time. Okay, we don't measure the time because the computing time is based on the CPU. But once you know the function evaluation and the gradient evaluation, you know exactly what the cost is, right? If you use the same program, you run it on my laptop or your laptop, it will take the same number of function evaluations and gradient evaluation, right? And that's the cost. We don't run program and then you see that the function evaluation and gradient evaluation are machine independent. It doesn't depend on machine. It depends on the algorithm or the code. So if you implement the code or the algorithm on different computers, you know, okay, it takes the same number of function evaluations and the number of gradient evaluation, and that's how we measure the cost. Okay, that's the. So today we finished the one-dimensional optimization, right? Also, you want the homework today or next Monday? You want the second homework too? You want it today or next Monday?